Phytoremediation, an environmental hope in soil contamination. In our era of globalization and mass industrialization, environmental pollution and degradation are major problems that affect anyone living in civilization. Recently, in the Los Angeles area, Vernon residents have been struggling with lead soil contamination from a former Exide Technologies plant in the community. It turns out since 2000, Exide's plant had been releasing cancer-causing lead and arsenic into the air, which later accumulated in the soil. This is just one example of a local soil pollution problem. Soil pollution can affect people through the soil water and leachate from it, or from direct contact with the dry soil contaminants. With air, climate, soil, and water all affected by different processes and contaminants, the need for cleanup and prevention methods has emerged. Phytoremediation has emerged as a method for cleaning up the environment through solar-powered interaction between plants, microbes, and soil. It could even be an important tool for dealing with lead pollution. Phytoremediation is biotechnology that uses plants and their associated microbes for environmental cleanups, like sites contaminated by inorganic and organic pollutants. Most common is a cleanup of toxic heavy metals like cadmium, selenium, lead, copper, zinc, that all cause central nervous system and cardiovascular system health problems. While research is underway, understanding plant metal tolerance, accumulation, and translocation is incomplete. Transcriptomics, proteomics, and metabolomics are necessary to understand phytoremediation connections between genes, proteins, metabolites, and metal ions. Phytoremediation entails different forms of sequestration, transformation, and degradation of contaminants in the soil. The process that is needed depends on the contaminant, plant, and soil type. The different forms of phytoremediation include rhizofiltration, phytostabilization, phytovolatilization, phytoextraction, and phytodegradation. Rhizofiltration uses plant roots in the rhizosphere to absorb, concentrate, and precipitate contaminants from water. Phytostabilization immobilizes contaminants by sequestering and releasing a chemical that converts contaminants into a less toxic state. Phytovolatilization happens through the uptake of contaminants by plant roots, then the release as volatile chemicals by either root or shoot evaporation and dispersion. Phytodegradation is the partial or complete degradation of contaminants by internal or secreted plant enzymes. Phytoextraction is the removal of pollutants by the uptake of the roots and sequestration of the pollutant in the plant's above ground shoots. Later, the plant is harvested for removal and destruction of accumulated contaminants. Concentrating on phytoextraction, its effectiveness is influenced by the factors of selection of soil site, metal solubility, and availability for uptake, and ability of plant to accumulate metals in harvestable plant tissues. Selection of soil site becomes important for the basis of phytoremediation because without an appropriate soil, the plant will not grow and cleanup will not occur. Soil science is crucial for the process in which soil cleanup criteria, soil bulk density, and particle size fraction must be considered. The soil cleanup criteria lets us know what level of risk a certain concentration of contaminant has been assigned. Risk varies with each type of metal, state regulations, and even specific land use. Soil bulk density is the mass of a unit volume of dry soil, which becomes important when measuring the soil contaminant concentration correctly for prediction of how many plants will be needed for cleanup. The particle size fraction must be considered as well because it is the particle size distribution of soil particles. For example, if particle size is larger than 2 millimeters, it is considered coarse fraction and would be less easily penetrated by contaminants. Brassica gentiana, also known as brown Indian mustard, is a common plant in the United States, and recently at a U.S. Environmental Protection Agency Superfund site in North Carolina, it was tested for lead phytoremediation. While it was determined that cheilites are important for the phytoextraction process, Brassica gentiana is a viable plant solution because of its high biomass, rapid growth, and ability to hyperaccumulate metals. We must consider both the advantages and disadvantages of phytoremediation when considering its use and effectiveness on a contaminated soil site. Disadvantages include that it is slower than immediate cleanup processes, since it takes time for plants to grow and certain plants could be seasonally dependent. In addition, biological methods are not capable of 100% reduction of contaminants. Also, phytoremediation may not be applicable to mixed waste or to soils besides the surface. Also, it is a new technology, so it does not have much research and economic data behind it. On the other hand, advantages include low capital and operating costs because of low plant watering and harvesting processes. In addition, it is a permanent treatment solution and can be done on site instead of transferring soil somewhere else. Comparatively, a typical excavation landfill soil cleanup method costs $150 to $350 per ton, while phytoremediation for a lead-contaminated site would cost $20 to $80 per ton. Taking all scientific, social, and economic factors into consideration, we can consider the utility of phytoremediation for soil pollution problems like that in the Vernon lead-contaminated community. Phytoremediation can be especially helpful in densely populated urban cities where it is difficult to extract all soil for cleanup. While cleanup is expected in Vernon, it is interesting to consider if plants could be used for ongoing phytoremediation to mitigate health impacts until further action could be taken.